In this video, we're going to build on our understanding of basic logic by exploring compound propositions. Then we'll walk through exactly how to construct a truth table to determine the validity of these complex statements using a few practical examples. All right, let's dive in. Compound propositions are simply statements formed by joining two or more propositions using logical connectives, such as negation, conjunction, or disjunction. Propositions can be represented in two ways, by a lowercase letter like P, Q, or R, or by a full sentence, such as 3 is an odd number, or the 4th month is April. For ease of evaluation, we assign a lowercase letter to each statement. For instance, we can assign P to our first statement and Q to the second. In formal symbolic logic, a proposition is compound if it contains one or more logical operators. For example, negation of P is a compound proposition. Even though it uses a single proposition, the presence of a logical connective, negation, will make it compound. Now let's see some examples. Here I have a logical expression written here on our screen, which states as P and Q in parentheses, which then implies to P. Before we start breaking this down, I encourage you to pause the video and think about how many possible combinations of truth and falsity we need to account for when we have two variables, P and Q.
All right, let's think about this together. Because we have two propositions, P and Q, the rules of logic tell us we have 2 to the power of 2, or 4 possible combinations of truth values. Whenever we have an n number of propositions, the possible truth value combination can be determined by 2 to the power of n. Let's say if we have 3 proposition, P, Q, R, then we'll have 2 raised to 3, which is 8 possible truth value combination, as shown here. But in our case, we have 2 proposition, P and Q, so it'll be 2 raised to 2, which is 4 possible combinations. So they could both be true, they could both be false, or one could be true while the other is false. Usually when we construct truth table, we follow a standard way, where we put true true, true false, false true, and false false. Now, when we look at a complex statement like this, we have to be careful about the order of operations, just like we are in arithmetic. If there are no brackets to guide us, we follow a specific precedence of logical connectives. If there is a bracket, we'll do it first. After the bracket, we always apply negation first, followed by conjunction and disjunction. And finally, we handle implication and by implication. For example, if we have a complex proposition such as this, first we'll do the negation in the bracket, negation of Q. Then we'll do the one in the bracket, R and negation of Q. Now we're left with implication and disjunction. Therefore, according to the law of precedence, we'll do the disjunction first, and then finally the implication. We have another example for you to practice, and maybe comment down below how you approach the complex proposition using the law of precedence. Here you might ask, what if we have conjunction and disjunction in the same proposition without bracket as shown here? When conjunction and disjunction, or implication and by implication, appear in a compound proposition, they're expected to be separated by bracket to give precedence for one of the two. Otherwise, it can't be solved for truth value since there's no logical rule of precedence for each pair. For instance, in the statement below, there is disjunction and conjunction together with no bracket. In this case, it's difficult to evaluate the truth value because there's no conventional precedence rule for such pair. Therefore, it is usually put in bracket to differentiate the precedent one, as shown. Coming back to our example, the brackets tell us clearly to evaluate the AND statement inside the parentheses before we move on to the if-then part. Hence, let's fill in our third column for P and Q. As we practiced before, a conjunction is only true if both parts are true. So for our first row, we get true. But for every other row where there's at least one false, the result is false. Now for the final step, the implication. We are looking at if P and Q implies P. Let me make sure I'm following this properly. An implication is only false in the specific case where a true hypothesis leads to a false conclusion. Looking at our first row, true implies true, which is true. In the other rows, our hypothesis is false. Interestingly, in logic, if the hypothesis is false, the whole statement is automatically true. So if you look at our final column, every single entry turned out to be true. In logic, we call a compound proposition that is always true a tautology, which we'll see in detail in the coming video. Let me give you additional complex proposition for you to practice, and I will put their truth table on the comment if you want to cross-check your performance. Feel free to pause the video. And we're done. Hopefully that makes some sense and gives you a repeatable understanding for building your own truth tables. If you found this helpful, definitely hit that subscribe button, and I'll see you in the next walkthrough where we'll tackle interpreting natural language into formal logic representation. Thanks for watching, and see you.